Okay, so I have to sort of get in the mode. I went through some of the things that I want to talk about. We'll talk about the energy stored in a dielectric. We had talked about this in the case of vacuum. So recall, the electrostatic energy was what? I think epsilon naught over 2 E squared d tau, right? And we talked about how the field itself stores energy. In this case, it'll be the energy density. And E squared, of course, is E dot E. Not that I wish to imply much more than what I'm saying, but recall how energy still has the form of 1/2 V squared M kind of quantity, right? So you'll get that kind of feature. This, of course, is in vacuum. We want to do the same thing in a dielectric. In a dielectric, it is a bit tricky. Now, suppose you have a dielectric material. Hey, James. Let me not make this diagram too exciting, but so here's my, and this might go all the way to infinity, and so this is a dielectric material over here. And there are some free charges that you bring to the surface or even within the dielectric. Okay? But the problem is, if you have a dielectric, these free charges induce a what? A polarization. And so you might get polarization charges. So this itself creates some sort of a polarization. You don't get to control those. That is in response to what you have brought. So what we're going to do, we only get to bring, so let me give it a title. We only get to bring some small free charge. In fact, it's small, delta rho f. And then we can take it from infinity and bring it somewhere over. That's not color-coded correctly. And then you can bring it somewhere over here and place it here, or even in the interior of the dielectric. So when you do this, you have to do some amount of work. Okay? The small amount of work that you do now, even the small delta F that you bring, delta rho F, small amount of free charges that you're actually allowed to bring, you may smear it all over the volume if you choose to. So let's assume we do that so that everywhere things have only incrementally changed. The work done is rho times potential d tau. Because after all, V is the energy per unit charge. At some point, we have to sum this up to get the total expression. So recall, the displacement vector satisfies divergence of D equals rho F. So we will, in this case, we will write this as the small change in D, correct? So I can replace this with the divergence in delta D. Now mind you, when I bring this charge, this potential is changing. But this is already an infinitesimal quantity. So if the potential changes to V plus some delta V, you'll have two infinitesimal quantities that you can drop because you're taking the limit as that gets to 0. Okay. And I'm going to use your standard trig identity to convert this into an expression we want. So the gradient of V times delta D, see this delta D is a new vector. It's a placeholder that will vanish very quickly. It's just a new vector, that's all. But we do calculus like normal. We do this as gradient of V dot delta D plus divergence of delta D times V, and that's exactly what we have. So now, I'll write this delta W to be equal to this guy first, divergence of V delta D d tau, all space, minus this guy, gradient of V dot delta D d tau. This is also all space, all over R3, if you will. This is a divergence. By definition, divergence of a volume is what? Integral. It's this defined on the boundary. Now, if we go all the way to infinity, we're not talking about a universe filled with dielectric material. So what happens to these two in particular, or rather even this in particular, would go to 0, right? At infinity. So this guy simply goes away when you integrate over all space. Using divergence theorem. And so we get delta W is equal to minus gradient of V is nothing but E dot delta D Now, we're almost there. If I can bring this delta out somewhere here, I'm done. I can remove the two deltas. That's a trick I use. So note, delta of, give it a little more space, delta of D dot E is equal to, first of all, I bring the epsilon out, and I get delta of E dot E, correct? Because D is nothing but epsilon E. And this I can write it as epsilon delta E dot E plus E dot delta. Or, these two are the same, 2 epsilon delta E dot E. Now I'm going to take this epsilon back inside and make it a D. Yeah? Notice this is what I have over here. So I can replace it as half of this. But the good news, delta W is equal to 1/2 delta D dot E d tau, and it's perfectly okay that I finish up here because I can hang on to the formula. All space again. And of course, gives us the expression this is simply the expression we need to compute the energy stored in a dielectric. Now, recall in vacuum, what is it? D is nothing but epsilon naught. And so you get the old expression back. So this is clearly a dielectric generalization of the previous case.
So we have our R going to infinity and vanishing that first term. The reason why we can't vanish the second term is because we're not evaluating that as a boundary, but that doesn't satisfy the
No, it's not a divergence of anything. We have to integrate over all space.
Okay.
Yeah, and sure, these things might vanish at infinity, but in the inside region, it doesn't vanish.
Yeah.
Okay, so let's try to understand how we might do a problem. So let me do example, I think it's 4.9 from your textbook. So what you have is a dielectric material of radius r. This is, of course, epsilon. This is epsilon naught. And so we'll assume that there is uniform free charges distributed over this dielectric. So we can use Gauss's theorem to compute the displacement vector everywhere. You have done this already, so I will call this as d in, and then we'll compute this integral, yeah? d in and d out, referring to inside the sphere and outside the sphere. And inside the sphere, there's a uniform rho f. We've done this a million times. It is using Gauss's law. You can verify it again if you'd like, but for our sakes, in this case, we're just going to proceed by copying down a previous result we have had. Rho f over 3 r cubed over r squared, r hat. Notice few expected features. Now, why is this 3 appearing? Because it's charge density. charge density is total charge over volume, 4/3 pi r cubed. And so that's at 4/3 showing up over, the 3 showing up over there. Outside, the displacement vector still goes as 1 over r squared. There it is. Okay. Let's write the electric field. After all, we need D dot E. So E inside, well, it's simple enough. It's 3 epsilon r. Yeah? And E outside is what? Rho F over 3 epsilon naught r cubed over r squared r hat. So then the energy stored is just difficult in terms of integrating the necessary terms. Oh, I should say that in doing this, I have assumed that things are a linear dielectric. Yeah, otherwise you cannot just read. In particular, I want you to read the argument that Griffiths makes on equation 4.57. Because we have assumed that D is equal to epsilon E. This is only true for a linear dielectric. And linear materials are the only materials we're considering, so I didn't state it separately. Yeah, linear. We have not studied nonlinear materials. Okay, so 1/2, I get 2 integrals. These are both r dot r, so I would get r squared. So let me pull out some factors. Let's do the inside part first. I have rho f squared over 3 and 3, 9 epsilon r squared sine theta d phi dr. I'm only going to write the r integral, but we know all integrals should be there. And then I want you to also tell me what these terms are and if I'm doing this correctly. So I would still get 1/2 rho f squared over 9 epsilon naught. I get r to the 6th, 1 over r to the 4th, r squared sine theta d phi dr. This is such a bad notation. Why? I didn't write any theta integral limits and phi integral limits. It's a sphere. Theta goes from, so, well, because I'm bothered by it, I'm going to write 0 to pi, 0 to 2 pi, and, this is not good, right? Let me write this in order as well. dr, d theta, d phi, dr, d theta, d phi. 0 to pi, 0 to 2 pi. Are we good? Yep.
Is our rho free constant? Is that what we're calling it?
Yes. So in this problem, we have free charges uniformly embedded. Yeah. That's part of the problem. So I get, are you clear about the two terms? For inside, I used epsilon. For outside, I used epsilon naught. And I also used the appropriate integral. I hope so. So here I would get 18 epsilon, 9 times 2, rho f squared. If I do sine theta, d theta, d phi, what do I get, Travis? Five seconds, integrate sine theta, d theta, d phi. I don't expect you to integrate, I expect you to know it. James? 4 pi. Yeah? Good. Then we have r squared, sorry, r to the 4th dr. Yeah? You don't have to do the integration. This is, after all, an adult conversation. Okay? Let me do it again consistently. 18 epsilon naught rho f squared r to the 6th 4 pi. What I'm then left with is integral of dr over r squared from r to infinity. Let's just do this part very quickly. This is minus 1 over r. Sorry, 1 over r to infinity. This is just 1 over r, correct? So I'm going to cancel the 2. I have 2 pi over 9 epsilon naught rho f squared r to the 5th.
Why epsilon naught?
Correct. Good question. Is everything else but epsilon correct?
Yeah.
Now, you know, these things that are so now what am I going to do? I'm going to put 1 over 5 times the dielectric constant. I don't remember these terms normally, but now that we're in the chapter on, when we were in chapter 5, I've forgotten this again. See the R? So this again becomes what? What's the only difference? Plus? That's it. And I hope the integral is correct so that I don't waste your time. And there it is. It is correct. I need to make a point because I want to explain the origin of an interesting phenomena. So I'm going to write, instead of writing it this way, I'm going to write 1/2 integral of d dot e d tau. This is the energy we found, right? It's simply that 2 pi over 9 epsilon naught rho f squared r to the 5th 1 over 5 times the dielectric constant plus 1. Again, as I use all these dielectric constants and whatnot, just continuously look up the definition. Yeah, maybe after this problem I might even state it one more time so that you remember it. But instead, if I use the old version, so I'm going to use the same definition, temporary notation. Griffiths in this problem refers to this as W2. It has no meaning outside of this example problem. But then, just for kicks, he says, let's compute this. Because this is what we would have done if we didn't know better. But clearly, you know how to integrate this because we just did d dot e, and e and d just refer by algebraic factors. But for completeness, I'm going to write this down. And he calls this W1. It is not very different. 9 epsilon naught rho f squared r to the 5th 1 over 5 er squared plus 1. And these two just change by a factor of er. Because in one case, it is e dot e. For every e, there's an er. So you get e dot e, you get er squared. That's what happens. And if you look at this closely enough, this is even smaller. So this number is bigger than this number. W2, what's the difference in energy? And he explains it in a wonderful heuristic way, but just to understand how the story is put together. And if you did the subtraction, again, I'm not going to do the subtraction, you find this expression. 45, that's because of this 5, 9 5s are 45, epsilon naught, epsilon r squared, rho f squared, r to the 5th, epsilon naught, epsilon r minus 1. And this is, in fact, greater than 0. So the old formula and the correct formula is, in fact, greater than the vacuum case. We know why. Because in the dielectric case, when you are bringing a free charge, what are you doing? Inducing more dipoles, right? And the dipoles have to stretch, which means it has to fight against the electrostatic forces in the molecule. I can't help, it's not luck. There is a deeper, we will actually compute, we'll model the molecule, and we'll compute it, and we'll look at the energy stored in the molecule and add it up. And if we're doing things correctly, what do you think we'll find? The energy stored in the molecules is precisely the difference. Yeah? I think I may have enough time. So a couple of things I want you to remind you. One is what? For this is epsilon E, and epsilon is epsilon naught 1 plus chi E, right? What is this? I forget. Not susceptibility. Is that what it is? Yeah. Correct. And this is permittivity. And then is what? The dielectric constants. And how did this whole thing come about? Because polarization per unit volume was proportional to the electric field, and we wanted to keep this epsilon, and whatever the factor was, that's what we called it. So that's how all these ratios kind of worked out. But while I'm doing this, it's kind of handy to recall another thing. See, these molecules, when you put subject to an electric field, they get polarized. And the more electric field there is, the more and more it gets polarized till it breaks out of its linearity property, right? But during that linear stage, it works exactly like a spring. So let's recall what makes spring a spring. So you have a mass, and this is the x equals 0 mark, and then you stretch the spring. Yeah, so let me do that over here. Now you've stretched the spring. And this is some distance, x. So what does the spring do? Pull it back. It's a restoring force, right? And F is equal to, this is called the spring constant. So if you have a force, a restoring force, that is proportional to the displacement, sort of like a bulwark, like a spring-loaded device, shock absorber. That is what we effectively mean by a spring. Remember all of that. I'll compute the energy stored in the spring. It's going to be this number. You can check it later on. I need space. Since I've started the story, I don't want to be sloppy, so I'll be very effective by going a little bit through my notes as well, so that all the terms, they're all proportionality constants. We don't want to lose any of them. So, first of all, look at a molecule being stretched by an electric field. Right? I'm going to write everything in magnitude. I'm not doing the plus or minus. It's a restoring force. Because the polarization is proportional to the electric field. Correct? What is polarization? It is the dipole moment per unit volume. I'm just going to write it this way. What is the dipole moment? Q times D. And this is d tau is proportional to E. And what is force? Force is proportional to E. Force is QE. So what do you find? The displacement is directly proportional to the force. So this is proportional to the force. So these molecules, at least for a linear dielectric, is spring-like. Okay? So let's do it this way. QE, that's the force on a dipole. That is a force on a dipole. Correct? And that's equal to some spring constant times d, all in magnitude. I put it's the molecular spring constant. And I very conveniently did not write the expression for, I erased the expression for the electric field for our problem. And I'm going to solve for K, so I'm going to write it this way. K is Q over D times electric field. Here, let me just do it this way. It is rho F over 3 epsilon. Watch, I'm only writing magnitude. The electric field itself is R hat, but K is a spring constant, it's a number, so just a magnitude. That's the electric field, okay? So that's this guy right here. Okay? And what I'm going to do is I'm going to multiply by d and then divide by d, because q times d is what? The dipole moment. And now I have to integrate over the entire molecule, because I don't know the dipole moment, I only know polarization. Polarization is proportional to the electric field. So then I write K to be equal to polarization times d tau over d squared rho f r over 3 epsilon. I want to be very clear. This is the electric field. This is the polarization. And you know that the work done, the energy of a spring, 1/2 kx squared, or in this case, d squared. So for us, that's perfect. Look, we don't know what this d is. You know, when Griffiths does it, it works out. Let's not do it, okay? It's going to screw up every single time. So let me get rid of the d squared, and I'm going to have, let me put this guy first, rho f r over 3 epsilon p d tau, and I have a d tau I have to integrate to find the energy stored in all the molecules. Okay. So now, well, that's good. We wrote this in terms of the polarization vector, but we know how that is related to everything else. Rho f r over 3 epsilon. Polarization is epsilon naught chi e times e. Rho f r over 3 epsilon. And then I have r squared sine theta d theta, or dr d theta d phi. Most of these things are trivial. Let's figure out what we can bring out. 1/2 rho f squared 9 epsilon squared epsilon naught chi e times 4 pi, and then r to the 4th dr, and I integrate over the entire dielectric material. Well, that's again, the 2 cancels, so I have 2 pi over 9 epsilon squared rho f squared epsilon, okay, let me do the integral first, r to the 5 over 5. I need epsilon naught chi e, correct? So from all the expressions that I have given, look at this, ER equals 1 plus chi e, so chi e equals ER minus 1. And you're gonna hate me for this, but you guys already hate me. I'm sure of it. Did I lose anything? R to the fifth over 5 epsilon naught. Are we good? And then what do we get? 2 pi over 9 epsilon. One of the epsilon naughts cancel. Rho f squared, r to the fifth. I can make it 45 epsilon naught. 45 epsilon naught. And then I have ER minus 1 over ER squared. This is not written clearly. Correct? And that is exactly, if you look at what we had. So forget the math for a second. What did we do? First, we show that the energy stored in a dielectric is 1/2 the integral of d dot E d tau. In the vacuum case, it is epsilon naught over 2 E dot E d tau. So then we did a specific example. We did a uniformly charged, free charged dielectric material, and we computed its energy using the old formula and the new formula. The old formula is just for charges. It doesn't look into the polarization that has been created. And we found the difference in energy. Then, using a heuristic argument, we modeled each of the molecules like a spring. The whole thing is heuristic, and then we argued that the work done is the energy of a spring. 1/2 kd squared. And we did convert that into an integral expression for this case, and we find that the difference in the formula, the old vacuum versus the linear dielectric, is precisely the energy stored in stretching the molecules. Kind of a very neat problem. We didn't have to know all the details about the molecules. We didn't have to know about the quantum mechanics of a molecule, what's going on, what the bond strength is. But for a linear dielectric, we know that the polarization is proportional to the electric field. And that's all we needed to know that it is effectively a spring. Sometimes nature gives us a break. It gives us a nice case scenario. Very often it does.